Thank you for attending this talk. So, I wanted to come back to a basic managing images because it's often an overlooked aspect of app development. It seems so simple that we don't think about it anymore when we develop our apps. But in fact, it can impact a lot the user experience if we don't take it seriously. So yeah, I will come back to really low-level basic stuff, but I think it's important to really use carefully the images in our apps. Also, I spend far too much time on this slide, so I wanted to let it run for a couple of seconds. It's built with Flutter, so yeah, enjoy. So I'm Aloïs. I'm a French developer. Sorry for my English. I'm not a native speaker, English speaker. I work for ClickUp as a staff software engineer. And I'm also a Google developer expert. I'm also, yeah. Does it work? Yeah. And I'm also a Google developer expert because of my open source contributions. I built, for example, Device Preview, which is a tool for previewing your app in other devices. So yeah, proud of it. So let's start with the basics of the basics of computer graphics, the pixels. As you may know, any screen is just a matrix of pixels which emits a particular color. The resolution of the screen is the size of this matrix. And the GPU is responsible for producing these colors, this matrix of color. The graphical processing unit is a chipset in your device, which is responsible for that. So it receives various types of data, and the idea is that it produces this matrix of pixels. The GPU is really good at parallel execution, but it runs only basic programs. It's really good at basic calculation, quick program that runs massively in parallel, as opposed to the CPU, which runs the main logic of your app, which is a long-running process. One common type of data that is uploaded to the GPU is the texture, raw texture data. And this texture will live in the GPU memory. And it's just a representation of what we see on the screen. So this a matrix of colors. And each one of these pieces of data associated to each pixel contains the color components for red, green, and blue, and potentially the alpha channel as well. The GPU can then sample this texture and decide to move it in a particular place on the screen. And yeah, it can change the size by choosing the right pixels, and all of that is done by the GPU. Flutter hides a lot of complexity with its engine, the Impeller rendering engine, which often transform many pieces of your application code into textures that are sent to the GPU. But it also sends textures that are directly your images, your assets, including raster images. So a raster image is just a texture that is stored into a file, basically. It's the same thing, but stored in a file ready to be loaded and uploaded to the GPU in order to be painted on the application canvas. Like that. So most of the time, it's first loaded into the random access memory and then uploaded to the GPU. Since an image is composed of tens of thousands or even millions of pixels, the amount of raw data grows rapidly, obviously. For example, if you compare these resolutions, you can see that the difference is huge between the three images, and we don't have an incredible image. It's quite normal to have a HD image, so 15 MB. If you have a photo gallery, for example, with a lot of images, you can realize that it could grow quite rapidly. So you have to be careful with it. Also, since it's uses a lot of storage, it's important to consider compression in order to save your storage before loading it on the GPU. And for it, you have various algorithms. But for example, if we take this simple example with consecutive pixels that are similar values, you could decide to group them and just prefix each group of pixels by the number of pixels, and you save a lot of memory. So it goes from 60 bytes to 17 bytes, for example, just with a simple algorithm like that, which works obviously just for this use case. But it's just an example of a compression algorithm, which is called RLE, for run length encoding, if I remember well. But obviously, you have a lot more evolved algorithms, like the one behind PNGs or JPEG images. And these images are first decoded by the CPU before being loaded to the GPU. Also note that even if they are compressed in the assets, once loaded, it will take the whole space into the GPU memory. So if you have really small assets and you load all of them and they are huge images, in the end, you could overload your GPU if you don't take care of that. Also, these decompressions particularly, takes a bit of computing process. So it's something to consider if you have a lot of images as well. But overall, today's hardware handled this pretty well, and it's not a big deal to. So you can use this kind of image without worrying too much about this aspect of computation. So also Flutter provide a basic widget to load this kind of images. Obviously, it's a common use case. So with the image widget and its underlying elements, the image element, it takes care of a lot of these steps, including with its image provider loading the image data, which can be compressed, takes care of decompressing, but also storing a version into the cache. So if you use a provider to load an image, and then the second time you reload it a second time, it will be loaded from the cache and not from the original source again. So that's interesting to have all of that included into the framework by default. And finally, it's the image element which paints the texture onto the Canva by using the reference into the GPU. So they are really simple, easy to use. So why you wouldn't use it everywhere? Because they have a couple of limitations and characteristics to keep in mind. First, since image is rasterized at a given size, if you display it in larger scales, you will lose data, obviously, because you don't have the missing pixels when you make it bigger, and the GPU has to interpolate each pixel in between, and that's why you sometimes end up with blurry results like that. And it's particularly visible if you use it on images that are illustrations with shapes, field shapes. You can notice on the sides this blurriness, pixelated rendering. And the good part is that on photos, it's a bit less noticeable. So if you download photos for a photo gallery, for example, it's not that important to have bigger image. I think it's pretty okay to use smaller image, even in larger scales. if it's reasonable. This is because a photo is just a sparse data, a lot of different pixels. So if the eye isn't able to detect if something is wrong between two pixels, it's a lot less likely to be noticed. So one solution to this problem is to simply provide different assets for different size. You simply create different variants of the same image, and you manage it at the runtime. For example, if you put it in a certain location in your app, you choose one image over the other. You could also use a layout builder to choose one image over the other, or other strategies like that. So this can be really tedious if you have different versions of your image to maintain and to refresh each time the designer delivers new designs. That's something to keep in mind. And also, you have to provide different variants for different pixel densities. If you want to ensure crisp rendering on various devices, you need to provide different versions of your image as well. You should know, but the pixel ratio is the number of pixels displayed for one given physical unit in the real world. So on two different devices, you could have two different screens with two different pixel ratio, and if you have a widget of a given size on one widget, it will have a different amount of pixels on the other device with the same size. So for that, you have a built-in system in Flutter to provide different assets in different directories, and it automatically loads the right assets given the pixel ratio of the device. Okay, so great. But what now if you want to update the image at runtime? One option is to use a shader. Because an image can be modified, doesn't contain any semantic information, so we will have to apply uniform updates to the entire image at once. So a shader is simply a small program that is uploaded to the GPU and that is then executed during the rendering phase of the application. And there are two main types of shaders, but the most probable to be useful from a Flutter program is the pixel shader. And the pixel shader is a small program that is executed for each single pixel of your application, of your Canva. So it takes a bunch of uniforms arguments, and for each coordinate of your screen, it will produce one different color. It can be by sampling a texture. A texture is also a uniform, but it can also be, for example, a color. If you want to recolor a full image, you give it the texture, the color, and for each coordinate, you will transform the color to match what you are expecting. So here is a quick example. One common example is to alterate the color of the image. This is a simple shader that changes the red channel of a widget or an image, and it's pretty simple. You can see you have the texture 2D as a uniform. You got the size of the image, and it uses specific Flutter pre-built configurations, but it takes the coordinates of the pixel, extract the color of the pixel in the original image, and then it multiplies the red channel by 0.225 to get a different version of the color. And it does that for every single pixel. So it's a really small program, and it's quite difficult to develop a shader if you're not used to it, because it's a different way of developing than a typical application, because you don't use if statements, for example. It's more like pure mathematical calculation, and it's something to learn when you first start using shaders. Fortunately, Flutter provides pre-configured pixel shaders, like, for example, the color filter or the image filter for doing blurs. So it's quite simple to change the color of every single pixel of an image with this. You can also pass a color directly to, the color directly to the image here. So 2 options, it's the same thing behind the scene, but yeah, quick shortcuts. But even if shaders are really powerful, Tim did a really cool liquid glass renderer, for example, which is really impressive. It still have a lot of constraints, and it's limited if you want to alter an image precisely. For example, if you want to change only the pink color at the bottom to a purple, like this, it will be really difficult to achieve this particular scenario with a shader. Simply because each pixel from the image is blend, so you can't really find an algorithm that would transform only some part of the image. And that's why a shader wouldn't always be a solution for it. One solution is simply like before, to provide different versions of your assets, pre-rendered, pre-rasterized. It's not great because it will increase your app bundle size. Not great for that, and also it's a pain to maintain, honestly. So if you have these kind of scenarios, I would probably more do layers. I would provide 2 different images and alterate the background image and keep the foreground image unchanged. That's one way to do it. It's also not perfect to maintain, but that might be useful in certain situations. So what if we could generate our image at runtime instead of trying to modify an existing image? That's actually what vector graphics images are. And Flutter provides drawing APIs to generate visuals out of nothing, just by calling APIs. So you have the Path API, which allows you to describe how to draw a shape on the screen. You have the Paint object, which allows you to give a style to a shape when you want to draw it. And finally, you have the Canvas. It's one of the basics of Flutter, where everything is drawn onto. With these three different APIs, you can draw a lot of things already. Obviously, you won't be able to generate a photo out of this, but or it will be really difficult. But it's perfect for drawing icons or illustrations, this kind of stuff. So, for example, if I want to draw art on the screen, you can see that I create a path, I move it to a first location, then I create a curve with different handle points to define the curvature of this curve. And I continue like that with many operations. And finally, I close the shape, and I have my shape that I then can paint onto my canvas. To draw it, I instantiate a paint, and I can define a style. For example, here I give a stroke style with a specific width, and I decide to paint it onto the canvas with the draw path method. You can also give a different style for filling the shape instead, and you can even give shaders. And for example, a gradient is in the end a shader, so you can instantiate a shader from a linear gradient or a radial gradient. If you wonder how Flutter does this generation, it's in fact done on the GPU by test by doing tessellations on the shape. So it tries to create vertices to create a shape built out of triangles, just like in video games. And that's how the first rasterized version of vector graphic is done. And if you're interested, I recommend you to check out this file in the repo to see which library is used for tessellation. It's quite interesting. And it's important to note that this step is done by the CPU. All the draw operations are first accumulated on the CPU and then sent at once on the GPU when everything is optimized at the CPU level. That said, we couldn't draw all of our icons and illustrations out of pure APIs like that. So that's why it's more likely that we will use a standard like SVG. SVG, because if you work with designers, you wouldn't have to. It's not realistic to translate all of their logic into code. So you will use a standard. The SVG standard is one of them, probably the most popular. It's a bit messy, but it works most of the time. So it's almost similar to what we've seen before. It's just like it uses strings, a specific format for the shapes, but it's similar to what we've seen before. You have move operations, move commands, you have curves command, line commands. It's exactly the same thing. You can then concatenate all of them into one string. It gives you a shape. And you have similar things to the paint, the paint configurations that we've seen before with the color, the fill. I don't see here, but I think it's fill color, and everything. So it's really similar. Also, it's a lot more. It's really big. It's a big standard. You have a lot of APIs into it, so that's why you often have different rendering if you render your SVG in the one navigator, in one engine, or another. It's because it's so complex that it's not covered by all engines. And that's also why sometimes you have to go into the design file to optimize yourself the files from the designer to make sure that when you export it to Flutter, it works as expected by keeping it as simple as possible by using all these simple operations. And SVG is quite lightweight. For example, this file is really lightweight, and if you would render it as a PNG, it would be a lot more because it's only composed of characters. As an example, here you can see the difference between a small image and a big image. You can see that you have a factor of 48 for the biggest one. So it makes a huge difference in the end for your asset bundle. So it's also something to have in mind when you include your assets into your package. So to render this kind of images in Flutter, you will need a specific package. It's not built into Flutter. You will need to add the Flutter SVG package. And this one will simply do what I previously presented. So it will parse the XML file and generate associated to the call from the Flutter API to draw the vector graphics on your Canva. So obviously, since it has to parse the XML files, it has a pre-processing step, and this one is not negligible. Sometimes when you have a lot of SVG files on the screen, you can see a small delay, and that's probably because of this XML parsing step. So I'm not sure if you heard about it, but there's also a different standard built by the Flutter team, which is vector graphics. It's a simpler representation, a binary representation instead of an XML version. So it's like a subset of SVG in a binary format. And the interesting part is that Flutter SVG is using this vector graphics library under the hood. So the first time that your SVG file is loaded and parsed, it will generate a binary version out of this parsing, and it will store it in your local storage, so that the next time it will load it from your vector graphics instead of the SVG file. But you could use vector graphics directly by yourself if you want to use pre-baked assets that are really efficient. You would skip the step of the XML parsing, and you would directly load your binary assets from it, instead of the cache like the SVG package. So yeah, I won't go too much into the detail for the binary format, but it's basically what SVG does. So you have consecutive bytes that are translated into commands and arguments, and it simply read byte by byte to generate the same thing that we've seen before. And the cool part is that you can use this package by yourself. You create a script, for example, to convert all your SVG file into vector graphics and put it into your assets. And this way, the first time that your asset is loaded, you don't have this XML parsing step and storage saving step. So it's a lot more performant, and sometimes you can you can save a few frames thanks to this transformation done beforehand. You also have an asset transformer which helps with this step, but I often prefer to have my own scripts because you have much flexibility, I would say. If you want to generate different version of an asset, for example, it's pretty cool. And you can write your script in Dart, so it's quite easy to do as a Flutter developer. Okay, so why wouldn't we use always vector graphics then? Because sometimes it's simply impossible. Like I've shown you before, the image with the gradients and so on blend together. You could do something almost similar, but it wouldn't be exactly perfectly the same. So for that, or for example, for photos, obviously it's not adapted. So it's really great for building illustrations or icons or this kind of dynamic images. One thing to expect also, if you use a lot of vector graphics on a single screen, you might expect janks because of this processing step of generating all these tessellations and potentially all the other operations required. So if I would have to summarize, I would say that rasterized images are great because they are simple to display, simple to load, simple for the CPU. For all of that, it's pretty great. But they are quite heavy compared to vector graphics, so something to have in mind too. Also, if you have a lot of variance, it's a pain to maintain, and it will also multiply your app bundle size accordingly. And same for alterations, for the colors. Like I said, if you have too much different variants, it becomes too tedious to maintain. On the other hand, vector graphics are great because they are lightweight, they are scalable. You can display them in any size. It will be crisp. They are dynamic. You can change the color of each part of an image dynamically. but they require an heavy computation from the CPU and potentially from the parsing if you are using SVG. So vector graphics are perfect for icons, logos, and for simple illustration, I said, because of these too much complex illustrations with gradients, mesh gradients, and all of that stuff. And rasterized images are great for photos or complex illustrations. And one last thing, I've started working on a small tool to simplify this process of maintaining images. I just want to have a bunch of SVG files as an input, and I don't want to care on when I'm developing if I should use a vector graphics or a raster image. So I decided to create a small tool that creates different things, including a sprite sheet out of all these images, these vector inputs. So this time it's really performant because one single texture is sent to the GPU and you just draw one part of the image on the screen. So it's great for icons, for example. And you can still alter the color. You wouldn't be able to change multiple colors on a single icon from this sprite sheet, but it's really efficient if you have a lot of icons in your UI. And it also generates all of the vector graphics assets so that if you want to alter the color with an animation, for example, or if you want to change the color inside of one particular vector image, you are able to because they are available. And it also generates the code associated to that because, for example, you need to know the coordinate of each image into the sprite sheet, so it will generate this part so that you only use a simple widget and you have everything ready in your app. So I covered really few low-level areas that wasn't directly related to images, but I really think that it's important to understand and learn about all this stuff to use well everything into your app and to understand how the shaders work, how they could be useful to you to make better interfaces. Also, how to optimize your apps so that you don't have too much jank when your first screen is launching for your user. So all of this small, that might seem not that important, but in the end, when you are developing, you are more. It's easier to realize what's important or not, or you could optimize. It's natural when you know all of that. Also, I'll keep you updated about the SVG bundle tool. It's not ready for production yet, but I will finish it really soon. And yeah, if you want to be noticed, you can follow me on X or GitHub, or I think that's all actually. Yeah, thank you. If you have any question, don't hesitate. Yeah, the mic is here.
So if
Sorry.
what do you do if you have a raster image and you want to resize it? Is there anything?
If you want to resize it in a smaller size
or a larger size or something, you have some.
To me,
is there any magic way of?
Yeah, you can do AI generation, for example. It's not incredible, but for small use cases, it might be a solution. Except from that, no, I don't think there are any other options that providing different variants of the image for different sizes. Yeah. No question? I can show you the code from SVG bundle if you want. Just need to change the share screen. How do you change? Yeah, here. Yeah, cool. So how you would use it is basically by running your script inside of this directory. Maybe you don't see a lot. Yeah, it's not great. Can you see or yeah? Fine. Okay. So basically, you run it inside this directory. You have a bunch of SVGs, SVG files. If, can I show you it here? No, it's not. So basically, this kind of image, icons, multiple colors. So different type of icons with different kind of. This one is with 2 colors, for example, with opacity. And what it does is that it generates all of these images. So for different versions, potentially, of your images as a sheet, and also for different densities. That's why it's useful, because maintaining all of that is a pain in the ass, honestly. So if you use this tool, you have all of that generated, but also the vector files in here. So if you need to render it in a bigger size, you can use the vector version. And finally, the code that is generated is looking like that. Oh, sorry, that's the use case. So it will generate an icons data with the reference into the sheet for knowing the specific position of each part of the image. It will also manage automatically the switch between the different images regarding the size of the of your element. So if it's a small one, it will use the small sprite sheet. If it's bigger than 24, it will use the 48 version, and if it's bigger, it will use the vector version, for example. So you have a bunch of automation like that. And yeah, that's it. And then you can simply use your widgets. Oh, that's the script. But yeah, more soon, I would say. So if you don't have any other question, I think we're good. And this is done with a shader, obviously. Just to reiterate.